Welcome to the CDG 3D Technology webinar program. Today's topic is the Figure-4 Standalone and how to 3D print parts in minutes, not days. My name is Grant Cameron and I am Director of CDG, the Concurrent Design Group. I'll be introducing you to the Figure-4 technology and then handing over to colleagues to run through a demonstration of the software, how to prepare a print, the 3D printing and post-processing. At the end, we will review the print times and answer your questions. Our case study for today's presentation is the 3-minute pen. We will be demonstrating to you the printing of this part, and after the webinar is completed, one of the pens will be sent to you as a free gift. To start with, let's talk about 3D Systems, who are the manufacturer of the Figure-4 technology. 3D Systems are a famous 3D printing company who have a large portfolio of 3D printers with different 3D printing technologies. 5 of their technologies are listed on this slide. CJP is most widely used for producing full-color 3D printed parts. MJP is a great technology for parts with no supports and no support scarring. SLS can produce sintered nylon parts, which are production quality for end-use applications. DLP and SLA are very similar in that they are UV cure resin systems. The difference being that SLA is able to produce very large parts. Let's just pause for a minute and think that if we were to design a new 3D printer, bearing in mind the industry is 30 years old, what would that 3D printer have in terms of its specification? We would want it to be fast. In fact, the fastest 3D printer. We would want it to produce high-resolution parts, to be easy to use, affordable in terms of the printer and the materials, able to produce a broad range of parts in different materials for both prototyping and production. We'd want it to be scalable and for the parts to be repeatable. We'd want it to be accurate and have a very high throughput. These are the thoughts that will have gone through the mind of this gentleman called Chuck Hull. You may know him as he is the pioneer and inventor of the world's very first 3D printer, a stereolithography machine, and this launched him to start up the company 3D Systems. The image at the top of the screen, called Figure-4, was an image on his very first patent for defining the process for UV curing a resin, and this is now the name of his latest invention. The Figure-4 is based on the DLP technology. So how does DLP work? Within the machine is a DLP projector, which takes the cross-sectional data from your 3D CAD file and projects the cross-section upwards through the projected light. This light shines through a transparent membrane, which is held by a tray in which we hold a liquid resin. The light causes a phase change from liquid to solid. The part is printed in layers and the build platform pulses up and down, each time coming back down between 10 and 100 microns short in order to produce the part. Let's have a look at the Figure-4 in action.
When my love takes me home, it's 105 in a 30 mile zone. Foot like clay, nerves like steel, wild ride when he's taking me. Can't slow down.
So one of the things the Figure-4 offers is ultra-fast print times. In the prototyping materials, it's possible to print up to 100 millimeters per hour in the vertical. For production parts, we're looking more like 65 millimeters per hour. In the chart on the top right, we can see that the grade 10 material can 3D print a part in standard mode at 103 millimeters per hour. And then the print times will vary depending on the material. Some good news is one of the very newest materials, Pro Black, is also equivalent to the grade 10 in terms of its super fast print speeds. Another key point with the Figure-4, it has a broad range of materials, so it then covers a broad range of applications. Figure-4 is extremely accurate and repeatable. So the repeatability means you can produce the same part over and over again, and it will be identical each time you print it. In terms of accuracy, we're looking at an accuracy of plus or minus 100 microns for a part size around 25 millimeters. Figure-4 is also capable of producing very complex geometry. In this slide, we're looking at parts with texture, which are very difficult to produce with other technologies, and in fact, even with injection molding. To produce a complex texture is easy with the Figure-4 technology. Another complex shape which is becoming popular is the use of lattices, and again, this can be produced with ease with the Figure-4. In terms of cost of operation, we need to look at the machine cost and the materials in comparison with other technologies. In this example, we are comparing the cost of production with a urethane cast process, which requires the production of a tool and then production of multiple copies of that part. So in the chart on the right, we can see it costs around $7 to 3D print a part on the Figure-4. This cost does not change when we increase the quantity. With a cast urethane production method, we have to pay for the tool, and then the cost of the parts comes down as we produce more. And we can see that if we're producing 25 parts, Figure-4 is still more affordable than a cast urethane process. In terms of scalability, Chuck Hull had thought through the whole process by producing a range of machines to match the production requirements of customers. The Figure-4 Standalone can produce around 500 parts a month. If a greater production quantity is required, we can step up to the Figure-4 Modular with a capability of 10,000 parts per month. If even greater production is required, the Figure-4 production system can enable customers to produce 1 million parts per year. Focusing on the specification of the Figure-4, the key dimension to highlight is the size of part that can be produced. On the Figure-4 Standalone, we have a maximum dimension of 200 millimeters, and on the Figure-4 Modular, this goes up to 350 millimeters. The layer thickness can be varied depending on part quality and also the required print time. Let's now look at the materials that are available on the Figure-4. There are currently a range of around 13 materials, and they can be split into different applications for prototyping, production use, or application specific. One of the first materials for the Figure-4 was the grade 10, and this is one of the high-speed materials. So if that is a key criteria, this is a good material to use, but for prototyping. In terms of cost, one of the lowest cost materials is the grade 15. If one wants high quality, high resolution parts, but then to produce a metal part, one can 3D print in a castable resin on the Figure-4. One of the key applications for this is for jewelry. In terms of engineering materials, the Tough Black 20 is a great material for producing high quality parts in an ABS-like material. If more flexibility is required, we have a couple of options for producing parts with properties like PET with Flex Black 10 or polypropylene with Flex Black 20. For a softer grade of material, we have a material called rubber black, which, as you can see in the video, is a material which can be very easily manipulated and it has a known shore hardness. Here's a small case study of producing rubber parts. With this build, we can produce 15 parts in an hour and a half at a part cost of between $1 and $2. If one needs an even softer material, then there is the option of using the Elast Black material. Some customers need a material with a very high end-use temperature, and this is addressed with the high-temp HT300 material. This material will go up to and beyond 300 degrees centigrade. For medical applications, there are two biocompatible materials. One is called MediAmber and the other is called MediWhite. The MediWhite is a very interesting material as it resembles the human bone in terms of color and material properties. It is in effect a ceramic-like material. An interesting application is the use of the eggshell amber material. This is not to 3D print a part, but to 3D print a mold in which silicon can be injected. The eggshell mold is then easily removed, leaving you with the silicon part. This is an excellent application for this technology. Here is a case study using the eggshell molding to show the production of hearing aids, and the key stat here is that the production capability was quadrupled using this technology. A new material which we really like is called Pro Black 10. The Pro standing for production grade. This material is very stable over many years. It doesn't UV degrade like many materials of this genre. The material is very high quality, very strong, and ideal for end-use applications. Here is a case study for the Pro Black material, showing two sets of parts being produced in an hour and 13 minutes. The average build time for a set of parts is 36 minutes at a cost of around $10. For end-use requirements in a different color, it is worth pointing out that the parts can be painted and they can also be plated. Just touching on the software application used with Figure-4 is called 3D Sprint. This is 3D Systems software application for all of their plastic printers. It is a very powerful piece of software which can take your 3D CAD file, repair it, set it up in the print orientation, add your support structures before printing. The software is very easy to use and very capable. In terms of the package, the Figure-4 comes with a complete set of tools that you require with the process, including the resin, the build plate, and a garage to store the resin in after use. Some accessories of interest are the UV oven for curing the parts and a material mixer for mixing the resin prior to use. Figure-4 can produce high quality parts very fast to enable you to maximize your throughput. Ways to maximize throughput include using one machine or multiple machines, or stepping up to the Figure-4 modular system, which is a semi-automated process. I'm now going to hand over to my colleagues Tom Preston and Alex Hall to talk you through a demonstration of the technology.
Hello everyone, my name is Tom Preston and I will take you through a technical demonstration of the Figure-4 system, starting from the setup of the machine, the printing process, and then the post-processing of the parts. To begin with, we're going to look at introducing you to 3D Sprint for setting up the print for sending to the printer. 3D Sprint is a very powerful software, importing native CAD files, enabling meshing of these files, repairing them using automatic repairing tools, placing them for maximum throughput, also generating support structures and sending to the print, and organizing the print schedule. To begin with, we're going to look at setting up the printer. So we can select the printer. You can see the Figure-4 system selected here. We can then choose our material. You can see all of the materials available for the Figure-4 system. The one that we're going to choose is the Med Amber 10. We can see the shading of the color. We can see the resolution from 10 to 100 microns. We can also see the print quality from draft to a premium quality part. We can see the build envelope here. We can then add in our part by dragging and dropping into the window. The loading is very quick on parts. So we can see the part in the build now. We can see that the part is highlighted in a red color. We can see that there is some issue with open boundaries shown by the part list. We can now look at the part in more detail. We can see the part here. We can zoom in, create a transparent view of it, and see that there is a problem highlighted in this area here. We are now going to perform a repair operation, so we automatically fix any issues with our part. So selecting the Fix tool checks for a number of things, including the open boundaries that we warned about. So clicking the Fix tool will fix all these problems and enable us, as you can see by the green tick, to be able to print this part. So now we add it back into the build platform. You can see that it's still highlighted in a red color. This is because it's not in the build envelope at the moment and therefore not printable. We now can orientate our part to be suitable for printing, either through an automatic method or by manual selection. So there are a number of different orientation techniques. For this part, I'm going to manually move the part to snap to a vertical position. So I can move the part around to 270 degrees, snaps to the build, and then we can rotate to a top view and snap it into the build, into the corner of the build. This will enable us later to maximize the amount of parts on the build platform. So I'm going to rotate to a better degree so we fit into the corner of the build. Very easy to do this process. Really nice and intuitive, very quick software. Just changing the color now to make it easier to see against the background. Looking at the bottom of the part, this is obviously upside down for the printing process. We're going to add the supports from the bottom. We can automatically generate support structure through an analysis and generation technique. The analysis tool allows us to know where the points should be, and then the generation tools allow us to generate the supports how we want them to look. We can also manually define points where support should be added. We can also erase these points if need be. So by clicking on the part, we can add support structures shown by the green points. We want to add enough points that we are holding onto the part as it's building. The supports attached to the build platform, whereas the part is always raised 3 millimeters from the build platform. This is to enable resin to refill the area of printing so that we ensure that the part has got enough resin to be produced. We can add all the points in the necessary position and then create the supports. You can see how quickly the supports are generated. Very easy to do. The main thing about DLP and also SLA technology is that we do not want to be starting from nothing. So what we refer to as islands. So now I will just do a quick analysis of the building layers to see that we are printing always from a stationary position attached to the bed. So we can now look at the build and see a Z-plane clipping, so seeing the layers that the machine will be looking at, and we can filter through the layers as it kind of prints. So we can see layer by layer what's happening, and that there are no islands apart from the bottom of the pen that are there. So it's always being supported from the base. You can now see the intricacy of the lattice structure inside the pen. It's a very complex structure, and it's easily printed on the Figure-4 system. Just looking at the bottom of the pen here, we can just have a look and see what the final area is going to look like. We can see that there's, as it's a pen structure, there's a hollow through the part, which is very nice because it allows for resin to fill really easily and no vacuum to form throughout the part. So now we're going to look at copying the part into the build envelope. We've generated the support, so the support will also be copied. So we're going to the top view and we're going to create a copy or copy part as such. So we can click on the part, create either by fill by pattern, which will fill the platform, or we can do a linear pattern, which will allow us to copy an array, so more control over the pattern creation. So we can see quickly a preview of how many parts are there and the gap between the parts. We can then reduce this to maximize the build usage. We always want at least a 0.1 millimeter difference between part to part to allow for the resin to flow back into the position. You can see that we are making a 9 by 5 filled platform. Easily done, easily spaced out. Very intuitively creating the amount of pens here. Again, just tweaking the value of gap between part to part. Nice uniform spacing. And then press, it's going to create it as a group, adding a group to the part list, and we can see that generating all of the pens now. So this is over 30 million polygons now, so it's quite a high number. We can obviously move these parts closer into the center of the build, making sure that it's going to be having enough resin flowing into all of the parts. We can then rotate around just to see what our build platform looks like. Obviously a huge amount of data here, and the 3D Sprint software is obviously handling this very well. So it gives us a real good idea of what's happening throughout our build. We can now hit a quick estimate of what's going to take for the build. So 3 hours, 51 minutes, and using approximately 320 grams of material. You can see all the details on the left, on the right side. We can then add this to the print, give it a name of the job. So we'll call this CDG webinar pens, and add that to the queue. So as it processes that, it adds it to the queue. Now it's sent down to the printer. We can then set off the print. So it's a very easy and intuitive process to set off the print. It's a very fast process. There's no waiting for the print to warm up. It's one of those machines where we can get it out the box and be printing within the same day. It's a really nice, easy to use system for setting off the print. So we're now going to hand over to Alex to prepare the print. So we're going to open up the UV filter glass around the part, about the print area, add the material into the print tray. So you can see the Med Amber 10 material being added. It comes in a very nice bottle, easily pourable into the print tray. You can see the levels, just the top there of the print levels, so we can see how much material is in there. We can now put the build tray into the build platform. We then use a plastic spatula to stir the material. So this ensures that all the polymerizing molecules are all mixed in evenly throughout the print resin. So you can see Alex is doing a very quick job of this. Very nice and easy process. We can just let the spatula dry now. Just let the last few drips come off. Brilliant. Put that to the side. Now we can close the lid back up. We can then move to the small LCD screen to the right-hand side of the printer. We can see the print ready to go. We can start the start button. We can confirm that we've got the correct tray in the printer. We can then scan the bottle to confirm the material. This is using a little QR reader below the LCD screen. It identifies the bottle, makes sure that we've got the right material. We then confirm a few things so that the print platform is empty and clean, the resin tray is full, and the resin has been stirred. And then away we go with the print. So initializes for a second, just processing the command, and then it will start to print. So the next thing we are going to see is a small time lapse of the printing process. So this is a really good demonstration of that oscillation of the print. So as it does this, it is recoating the film with fresh resin. It's not a tearing action that you would sometimes see with other systems. It is always free to move up and down. There's no tearing to remove the parts from the film. And this is due to the very smart and intuitive film at the bottom of the tray. Where the UV is projecting onto the tray is a semi-permeable plastic, which allows for oxygen to flow through the plastic, meaning that there is no stress on the part. So it's always free to move up and down, which is really nice because it enables us to print a vertical part with very little stress, very little support structure. It's a very quick process. Again, we're printing at 50 microns. This is a 4-hour print condensed down into a 2-minute video. Very, very simple process. Again, really nice and simple with the fact that there's only one moving part on the printer, which is this moving up and down motion through from the gears there. So this is a very reliable system, meaning that there's only electronics other than this one moving part. It's obviously a nice, simple machine, low impact in the room. We have it stationed so that it's very kind of succinct as such. We have the cleaning station next to it. It could be put into a separate room just to, or even to a broom closet or something like that, because of the ease of use and low requirements of the machine. It's got its own carbon filter and particulate filter for ensuring that the print envelope is clean, and also the projector is clear of any dust. As you can see, we're almost finishing the print now. Very fast again. It's a really nice machine, really low impact, really easy to use. As you can see, the finish there, last few drops coming off the print there, ready to be processed. So moving on to the post-processing, we look at removing the print platform from the printer, rinsing the excess resin off of the parts in a 2-stage wash. We dry the parts off and then we UV cure them. So Alex again now taking the print off the machine, easily taking the magnetically attached tray from the build, letting the last few drops come off, moving to the clean station. We then look at the ultrasonic tank here with our cleaning solution in. We take the pens and we use the specially designed tool for poking through the attached resin at the bottom here. So there's no scraping that you might see on other systems. It's a very easy tool for just taking them off of the build. See how they drop into there. So now we're ready to set off the ultrasonic tank. We set this for 20 minutes for this many parts, but for a smaller amount of parts, you can reduce the time for this. So we now take the tray of pens and we take it to our secondary rinse station. So moving across, we move to the rinse station. We just drop them into the rinse station, so we can drop them into there. Very easy, nice process. Put the tray back into the ultrasonic. So the rinse station is all it's doing is a water for rinsing off the solution that we use to get the excess resin off. So this ensures that the parts are nice and clean. We also use this time to take off the supports. So again, the supports are so minimal, very low attached pin prick points that they're really easy to take off. And they leave little to no scarring on the part. So as you can see, we leave them to dry after this process. So we dry them off and then we can put them into the UV tank. The UV tank is used to post-cure the parts. We call them green as they come off the machine because they need an additional amount of UV light to get the full material properties from them. So we cure them at different amounts depending on the different materials. So you can see here that we spend 60 minutes on the med amber material to get the full material properties. But we also have materials like the grey 10, grey 15, which take 15 minutes to cure. So different materials have different cure times. So this is the finished example of the pen. You can see it compared to one of our traditional pens. You can see the complexity of the pen here. So this is the giveaway for joining the webinar today. So you should be receiving this in a short amount of time. So now let's have a look at the stats for printing these pens off. So we're looking at what would be the general costs for printing of something of this sort off. So looking at prototyping of the single part, we are saying 50 micron accuracy, very high resolution. The med amber 10 material, the print time is 3 hours 51 minutes, and the material cost is £2.49. The time per part again is 3 hours 51, but for a prototyping, this is still very, very quick. So let's see what we can do for productionizing something of this quality. So let's look at a quantity of 6 off. So again, same print time. Again, because of the printing technology, we're projecting the whole layer at a time. So there's no slowdown for filling the whole bed with parts. So we really can use it as use as much space as we want, so we can fill it up and still take this minimal amount of time. So again, the material cost each is about the same, £2.49, but the time per part is now 38 minutes. So this is a really good idea of what we can achieve with just a small amount of production. So let's see for this demo, what did we spend on each pen? So 50 microns, 3 hours 51, £2.49 each, 5 minutes per pen for 45 pens. So this is a really good this is a very nice sparse amount of pens really. So what can we do to maximize the build envelope? So let's see, we can put 60 into the build envelope. So this reduces the time down to 3 minutes and 50 seconds per pen. A really, really quick process. Now, this is actually one of the slower materials that we have on offer. So let's see what we can do with materials such as Pro Black 10 at 100 microns. This is a very fast material with a higher resolution. We can reduce the print time down to 1 hour and 22 minutes for 60 pens. At £2.42 each, again, a reducing cost for this material. The time per part is 1 minute 22 seconds. Very, very quick. In fact, it means that we can produce 1,000 parts in 23 hours, less than 24 hours. This is amazing compared to a traditional aluminium tool where 1,000 parts would take 2 to 3 weeks to produce. So moving on, we can see what the affordable comparison would be as well. So down to £1.72 using the grey 15 material. So a very cost-effective material as well. So having a look at a comparison chart to other 3D printing technologies, so we can see that the DLP technology is very, very quick. So 12 off of these pens would take approximately 82 minutes. So this is a very, very fast technology. If we compare it to SLA, it's still 4 times faster, taking on average 6 hours to produce this many parts off. Compared to the MJP technology that we mentioned earlier, this is a low support structure method of printing, but takes 12 hours to print. So we're 8 times faster. And then SLS and FFF, we're 15 times and 70 times faster with the DLP. So the Figure-4 standalone DLP printer is the fastest additive manufacturing technology on the market.